Hello, this is Greg Bauer, and we're going to look at confidence intervals in a statistics class. So let's start with an example, and by way of introduction, suppose you hear that 17% of teenagers consider suicide yearly. Now, this would be quite difficult to ascertain such a number, and you wondered, how accurate would it be? How do you know it is accurate? Now, no one has asked all the 30 million teenagers in the United States about whether they consider suicide. But let's say a diligent researcher carefully asks, and you got to be anonymous and be really careful how you ask the teenagers. 3,000 teenagers, let's say, are asked. The proportion of teens asked out of the 30 million is 3,000 divided by 30 million, which is 0.0001, or if you move the decimal place over two places, 0.01%. So that's 1/100th of a percent of the U.S. teen population has been asked. Will this be at all accurate? Well, the answer is yes, it will be fairly accurate. And we're going to look at, how they determine accuracy for situations like this where they're asking yes or no, have you considered suicide, and figuring out that percentage. So this is from section 7-1 in Triola's textbook, estimating a population proportion. Now the key concepts, first of all, you need to realize that the sample proportion p hat is an unbiased estimator and is the best single point estimate for the population proportion p. So unbiased estimator means that it's good at estimating the population value. So the population proportion is like, for all teenagers, what percent have considered suicide? And the sample proportion was just from those 3,000. So, but the sample proportion is the best estimate, point estimate for the population proportion P. Now, the sample proportion is then used to construct what's called a confidence interval for the population proportion P, which, if we have a good sample, should contain this parameter. Now, in this section, we also will determine the sample size necessary to ensure a certain degree of confidence that the parameter is within the confidence interval we create. So how big of a sample do we need to give us a certain margin of error or a certain precision in our confidence interval? So what is a confidence interval and what is it used for? Well, confidence interval is a range or interval around the point estimate. The point estimate in this case is the sample proportion that is used to estimate the true yet unknown value of a population parameter. So that's what a confidence interval is. It's a range or an interval that tries to estimate a population value. Now, first of all, there's an idea called the confidence level. It's a high probability, such as 95%, that's chosen to represent the probability that a confidence interval created from a sample proportion or mean will contain the population parameter. Now, it's assuming that the estimation process is repeated with a number of times. In other words, you take a sample, you calculate your point estimate, and you create your confidence interval, and you do this a large number of times, and so 95% would mean 95% of the time our confidence interval contains the true population parameter. Now, a Greek letter alpha is used to represent the probability that the confidence interval does not contain the parameter. Then the confidence level is 1 minus alpha. So if the confidence level is 90%, or 0.9, then our alpha level is 1 minus 0.9 or 0.1. If our confidence level is 0.95, then 1 minus 0.95 would be 0.05, and that would be our alpha value. If our confidence level is 99%, then 0.99, and so you subtract that from 1 minus that, and you get 0.01. So alpha value is sort of the opposite of the confidence level, all right, in terms of one minus the other. Now, here's an example. So a 95% confidence interval estimate of the population proportion P of those who text while driving is found to be the interval from 0.205 to 0.235. Now notice P, the population proportion, we think is inside that interval. Now that's based on the point estimate, P hat, of 660 divided by 3,000, or 0.22. So this is like in the scenario where you sampled 3,000 people and asked them, do you text while driving? And 660 of them said yes. So this is a yes-no situation where you're only getting qualitative data, yes or no, and then you take and say how many said yes out of the total number in the sample, and it gives you a what's called a sample proportion. So that means 22% text while driving, or admit that they text while driving. Then from that, you would build your confidence interval. Now, we can say that we're 95% confident that the true population proportion of people who text while driving is between 20.5 and 23.5%. And that's from these 0.205 and 0.235. This means that if many samples of size n are taken, of n equal 3,000 are taken, and you make a whole bunch of confidence intervals using this method, 95% of these confidence intervals would contain the true population proportion of those who text and drive. So I've got what's called StatCrunch up on the screen now. And so this illustrates what I've been talking about. So suppose you create a lot of confidence intervals, and the true population proportion is 0.5. This is like flipping a coin. You would expect that 50% of the time of the whole population of trials, 50% of the time you would get heads and 50% tails. So that's like your population proportion. Well, if you did a sample of 30 of these and then estimated the sample proportions, and then created from that confidence intervals, most of them, about 95% of the time, your confidence interval, like this one here, that has a sample proportion, or p hat, of 0.533, and the lower limit 0.355 and the upper limit 0.712. And you notice that 0.5 is inside between the lower and the upper limits. And so that confidence interval contains the population proportion. But these two here that are red, and this one, all the ones that are red did not. So in this case, we had 4 out of 100, or 4%. But on average, I mean, if you do this again, I can hit refresh and it'll do this again. This time, we didn't have any that didn't contain it, which is unusual. This time we had 1, 2, 3, 4. Let's see. Sometimes you'll have more than 5. Okay, so this one had 1, 2, 3, 4, 5, 6, 7. So sometimes it'll be more than 5, and sometimes it'll be less than 5. But on average, it'll be 5 out of 100, or 5% of the time, our confidence interval will not contain the true population value which in this case is 0.5. So I hope you understand what I'm talking about here. So back to the PowerPoint. At the bottom of the slide, it gives some incorrect interpretations. There is a 95% chance that the value of P, the population parameter, falls in between 0.205 and 0.235. This is not correct because the population parameter does not fall. The population parameter is not moving. It's fixed. What is changing is the p-hat values, the sample proportions, and the confidence intervals. Those are moving, and so the confidence interval is falling, and sometimes it'll contain the population parameter and sometimes it won't. Another incorrect statement is 95% of the time p-hat falls in between the two ends of the interval. Again, this is false because p-hat is always exactly in the middle of the confidence interval. In fact, we use p-hat to create the confidence interval. We start from p-hat and go down and go up from that to create the confidence interval. All right? Now, a critical value is a number, often a z-score, that will separate sample statistics that are likely from those that are unlikely, according to our desired level for alpha. Now, the critical value, z alpha divided by 2, is the z-score separating scores so that the area alpha divided by 2 is in the tail to the right of the critical value. So alpha is the probability that that it falls outside the critical values, and when you have a 90% confidence level, then your alpha value is 0.10. It's always 1 minus that, and then your alpha divided by 2, or area under one tail, is half of that, so 0.1 divided by 2 is 0.05. So what this means is the confidence interval or level is 90%. That means 90% of the time it falls. Your 90% of the time it will be between here, the two critical values, and then 10% it'll be outside that, and 5% will be above, and 5% will be below. So you just take alpha and divide it by 2 to get the upper tail or the bottom tail. Now, the critical value of 1.645 is the z-score that cuts off that top 5%. Now, if it's 95%, the alpha level is 0.05, and you cut that in half, so it's 0.025 for alpha divided by 2, and so the z alpha divided by 2 critical value is 1.96. So that means that if you're out here at 1.96, then it'd be 2.5% in the upper tail and 2.5% in the lower tail. So if we want to be 90% confident that our confidence interval contains the population proportion P, then our confidence level is 90%, or 0.9, and alpha is 0.1. The area in each tail would be half of that, so 0.05, and our critical value would be 1.645. All right, as I explained. Now, if you have a higher confidence level, so let's say 99%, your alpha level would be 0.01. That's 1%. Your alpha divided by 2 would be 0.5%. 0.005 is 0.5%. So you need a bigger critical value. You need to go out here farther so that the area under the upper tail is just 0.5%, and out further this way, so a bigger negative number, so it'll be like negative 2.575, and that will be a 0.5% in this tail. All right. Now, what if you wanted to find other critical values than the ones in the chart? Well, you can use the norm.inv command, which is an Excel command. So here's an example. Find the critical value z alpha divided by 2 associated with a confidence level of 94%. So since the critical value is 0.94, then alpha has to be 0.06 because 1 minus 0.06 is 0.94. And so 6% is the area in both tails. So if you divide that by 2, you get the area in one tail. So the area to the left, so if it's 3% to the right of this critical value on the upper side, then it's got to be 97% to the left of that. So in your norm.inv command, you say norm.inv 0.97, comma 0, comma 1. And that will give you the critical value. Now it rounds to 1.881, and you can check this by finding the area in between the negative and the positive of this critical value. So if you do norm.dis 1.881 minus norm.dis negative 1.881, then you should get 0.9400. So that's typical of how you find the area in between two values. These are z-scores. Okay, now margin of error, we denote that as E, is the difference between the point estimate and either end of the confidence interval. So from the point estimate, which is p hat, if you measure the distance from that to the upper end of the interval, then that would be E. Or you could measure from the middle to the lower end of the interval, and that would be E. All right. It is found by multiplying the critical value, z alpha divided by 2, with the standard deviation of the sample statistic. Now that's also called the standard error. And so you go the critical value times the standard error. We have square root of p hat q hat over n. And q hat is 1 minus p hat. So here's an example. For a 90% confidence level, find the margin of error if p hat is 0.34 when n is 500. So your sample size is 500. Now from the table, for a 90% confidence level, our critical value is 1.645. We talked about that table. 1.645 is for 90%. Now the standard deviation sample statistic, in other words your standard error, is square root of p hat q hat over n. And p hat was 0.34 in this example, and 1 minus 0.34 would be 0.66. So square root of 0.34 times 0.66 over 500. That is the calculation, so you get 0.02118. So the margin of error, so that's the standard error. So you got to multiply, according to this equation, the critical value times the standard error. So the critical value, 1.645, times the standard error, 0.02118, and you get the margin of error, 0.03485. Okay, now I carried it out one or two more digits past what I needed to, but this gives an accurate margin of error. Now the conditions for using confidence intervals for a population proportion. Number one, the sample has to be randomly selected, or be a simple random sample, preferably. Now, item 2, it has to be responses from a binomial variable. In other words, there's two choices, yes or no. Okay, so this is perfect for polls where they ask, will you vote for someone, yes or no? Do you like pizza, yes or no? Do you text while driving, yes or no? So it's qualitative information, and it has to be binomial. You can't have 3 or more choices. And then you have to have independence, and that's where the population has to be at least 10 times the sample size. All right, so item 2 also has that. And then item 3, there has to be at least 5 of each choice in the responses, or using math, you could go n times p hat. That has to be greater than or equal to 5, or n times q hat has to be greater than or equal to 5. Both of those have to be true. And that ensures that the distribution of p hats is approximately normally distributed. All right, so here are the procedures for constructing a confidence interval for a proportion. First, ensure that the conditions are satisfied. Second, determine the critical value using the table or norm.inv as we showed you. Third, evaluate the margin of error as above. And then use the point estimate p hat and e to create your confidence interval. So you're going to go p hat minus e is less than the population parameter, p is less than p hat plus e. In other words, p, the population parameter, is in between but the two ends of the interval. We trust 95% of the time, or whatever, or 90% of the time it will be. Now you could also go p hat plus or minus e like that, or in this notation with the inside parentheses. So for the example up above, for the 90% confidence interval, we had a p hat value of 0.34, we had a margin of error of 0.03485, and then when we subtract that and add that from the p hat, you get these two ends of the interval. Okay, now we're going to look at Excel. How do you use Excel to do this? First, you must know the type of confidence interval you're doing. In this case, it's a 1 proportion z interval, because we're basing on the z alpha divided by 2 values. Second, for this CI, there's not really a shortcut. You got to use the margin of error formula. You got to take the critical value times the standard error, and you can click on empty cells and put them in there, or you could just, one big long formula here. This gives the critical value, if you know alpha, and also it gives this margin of error, standard error, the square root of p hat times q hat, which is 1 minus p hat, and then divided by n. And then you do p hat plus or minus e, or p hat minus e, p hat plus e. So I'm going to show you that using Excel. So this example says, suppose you ask 200 adults whether or not they shop at a big warehouse store such as Costco or Sam's Club, and you find that 88 do so. Find a 95% confidence interval to estimate the population proportion of all adults who shop at these stores. So the sample proportion, first of all, that's your point estimate. That based on the sample, what proportion shop at these stores. So that you would say simply equals 88 divided by 200. So that is your p hat. How many said yes out of your total? All right. So that is 44%. Now your critical value can be found from the table, because 95% is your confidence level. And so we said that that had a critical value of 1.96 from the table. Okay. Now you could find that with an Excel command also, but you're going to go equals norm.inv, because you're trying to find a z-score with a certain probability, and you're going to go 1 minus 0.05, which is alpha. If your confidence level is 95%, then alpha is 0.05, but you got to divide that by 2 to get the area in just one tail, not two. Anyway, you have that, and you hit enter, and it gives you the 1.96, but we had the table value to know that anyway. Now your standard error is that square root of p hat q hat divided by n thing. So you go equals SQRT parentheses. Now you got to go p hat. Now p hat is located in cell B6. So B6 times, you're going to use an asterisk for that, parentheses 1 minus B6. So that's the Q hat. 1 minus P hat is Q hat. And then divided by N. Now N is 200. And so do that, and you get what's called the standard error, which in this case is 0.0351 approximately. So the margin of error, you can just multiply the critical value times the standard error. Critical value is in B7, and multiply that times B8, and that gives you your margin of error. So it's 0.06879 or whatever you can want to round it to. All right, so now the lower end of the confidence interval, you're just going to say, I'm going to take the sample proportion, that's your point estimate, 0.44, that's your p hat. So that's in B6, and you're going to, for the lower end, subtract the margin of error, which is in B9. So B6 minus B9. And then in the for the upper end, you're going to take B6 and add B9. So that is your confidence interval. So what this interpretation is that we are 95% confident that the true proportion of all adults that shop at big warehouse stores is between 37% and 51% approximately, or 37.12% and 50.88%. Okay, so that is the how to find a confidence interval for a proportion, population proportion. So the suggested steps in Excel are basically what I just did, but step 1, place p hat in Excel, number of yeses divided by the total. 2, place the critical value into another cell from the common ones, or you could use the norm.inv command. 3, place the standard error into another cell using square root of the p hat times 1 minus p hat divided by n formula. And then 4th, place the product of these two things to be the margin of error. Product of the critical value and the standard error. And put that into another cell. And then last of all, you're going to do the lower end and the upper end. So go p hat minus the margin of error and p hat plus the margin of error into two different cells to find your confidence interval. All right. So that's a summary of the steps for Excel. Now, sample size, determining sample size. How big of a sample do you need? So let's say you wanted to pull Mercer students and get the percentage of Mercer students that are, I don't know, that are women. Okay, the percentage of Mercer students that are women. How would you do this using a sample? How big of a sample would you need? Let's say you wanted to determine the percentage that are women all the way down to 2% margin of error. Okay, you need it within 2%. How would you do this? Well, you need to either know what p hat is, the approximate number of women, or use this second formula over here. So if you knew what p hat is, let's say you knew that there's approximately 70% of women at Mercer or 60% of women at Mercer. So you could use p hat to be 0.6. Q hat would be 0.4, 1 minus p hat. And then the critical value, that depends on your confidence level, but figure out the critical value, square that, and also square the margin of error and put it on the bottom, and you just divide that, and it comes out to a value for n. Now, if you don't know what p hat is, then you can just use 0.25 here, and it's going to give you maybe a slightly larger sample size than you might want, but it'll give you approximately a good sample size. Now, we talked about sampling confidence intervals for population proportions. And that's for binary, categorical, like yes, no, male, female, whatever situations. But this new section, section 7.2, uses confidence intervals to estimate a population mean when we're talking quantitative data. So when you have quantitative data, numbers, and you want to estimate the population mean. So for example, let's say that you wanted to know the average age of people who live in Atlanta area. Okay, so the average age of all people who live in Atlanta, that would be your population mean, mu. Okay, so we would use a sample mean, x bar, as a point estimate for that. So we would take a sample and ask people what their ages are and find the mean of the sample, and that would be x bar, but that would be our point estimate for the population mean. Okay. Now, there are two cases when we talk about quantitative situations. Sometimes you know the population standard deviation, and sometimes you don't. So, but let's talk about conditions now. So the conditions for constructing a confidence interval for a mean in a quantitative situation are, the first two are pretty close to the other that we talked about with proportions, but the sample has to be randomly selected, preferably a simple random sample, and then the sample has to be independent. Now that means that your population has to be at least 10 times your sample size. And then the third condition is you have to have the x bars, the distribution of x bars called the sampling distribution, that should be normally distributed either by the fact that the original population was normally distributed or the sample size was greater than or equal to 30. So if your sample size was at least 30 or the original population was normal, then you'd have that condition met. All right. Now, the first case is when you know the population standard deviation, and so this is actually a more rare situation. Often you will not. But you can find it's a little bit easier to do this type of confidence interval. So here's an example. To find the mean age of Atlantans, so we talked about this already, a research group calls 500 random numbers in the area. The sample mean age comes out to 39.4, let's say. So let's say that you take a sample of 500 Atlanta residents, and the average age is 39.4. Now, from earlier studies, the population standard deviation is known to be 15.8. So let's suppose that you've done this before and you know the population standard deviation is always 15.8 or close to it. So you this is a situation where we know the population standard deviation. So it asks you to construct a 90% confidence interval to estimate the population mean. So here are the steps. Step 1, ensure that the conditions are satisfied. Okay, number 1, do we have a random sample? Yes, it says the research group called 500 random numbers. Do we have independence, which means are there more than 10 in the population, more than 10 times the sample size? Well, the sample size is 500. 10 times 500 is 5,000. Are there more than 5,000 people that live in Atlanta? Well, yes. There's millions that live in Atlanta. And then thirdly, the normality condition, we have to know either the original population was normally distributed or the sample size was at least 30. Well, we have the sample size is at least 30. So we're good on the conditions, all right? Then you determine the critical value using the table or norm.div. Now we're constructing a 90% confidence interval. So we're going to use a critical value of 1.645. That's for the 90% situation. That's from the table, all right? And then we're going to calculate our margin of error. Now we need to know this sigma divided by the square root of n. We've got the critical value, but the sigma divided by square root of n. So I calculated that. I took the standard deviation, 15.8, and divided it by the square root of 500, the sample size. So 15.8 divided by 500, and you get 0.707. And then the margin of error, just multiply your critical value and your standard error, and you get 1.16. So then when you have calculated the margin of error, then you just do x bar, the sample mean, minus the margin of error, and x bar plus the margin of error, and that is an interval that you hope the population mean, mu, is inside, okay? So you just go x bar minus e and x bar plus e to find the two ends of the interval. And so that's what I did here, 39.4 plus or minus 1.16, and it gave us the low estimate of 38.24 and an upper end of 40.6 or 56. So we are 90% confident that the true average age of Atlantans is between there. So to use Excel to find a confidence interval for a population mean, when you know the population standard deviation, that's going to be a one sample z interval. So first you want to determine what type of confidence interval you're doing, and this is going to be a one sample z interval. And there's a command called confidence.norm or confidence.t if it's a t interval. We'll talk about that later. But you'd use this to find the margin of error. So this is like a one-step way to find the margin of error rather than multiple steps like we did before. Now the confidence.norm command, it needs you to tell the significance level or the alpha level, which is 1 minus the confidence level. So it'd be 0.05, for example, would be a common one. And then the population standard deviation sigma, and then the sample size. So I've got it in words over here. Now, once you find that margin of error using that confidence.norm command, then you find the two ends of the interval, and you can place them in separate cells here, as I mentioned. And then if you do not know the population standard deviation, that's when you're going to use the confidence.t command, and we'll talk about the t distribution in a moment. But instead of using the population standard deviation, you're going to use the sample standard deviation, S. All right. So let me show you how to use that or do that in Excel. So here is an example. Suppose you want to estimate the average height of 6th graders in a school district. So you randomly choose 8 schools in the district and 20 6th graders from each school. So you've randomly chosen 8 times 20 or 160 6th graders from the district. So you find that the mean height of those 6th graders is 52.3 inches. But you know from past experience that the population standard deviation is always 3.6 inches for 6th graders. So determine a 92% confidence interval to estimate the mean height of all district 6th graders. All right, so that's the problem, and you first of all start off by listing the sample mean. Well, we know what the sample mean is. It's 52.3 inches. Okay, they gave us that in the problem. Now the critical value, well, this confidence level 92%, they don't have that's not in the table. So you're going to have to calculate the critical value using the you're gonna have to use the norm.inv command. Okay, so equals norm.inv, and then we're going to go, the probability was going to be 1 minus alpha. Well, what is alpha if you have a 92% confidence level? Well, alpha is 0.08, and because 8%, 1 minus 0.92 is 0.08, and then divide that by 2, and then you have a mean of 0 and a standard deviation of 1 always for z-scores. So right there, that gives you a critical value of 1.75. All right. Now for the 90% confidence interval is 1.645. So this is a little bit higher than that. Now your standard error will be the standard deviation, population standard deviation, divided by the square root of n. So you'll go equals the 3.6 divided by SQRT of the sample size. Now, how many are in the sample size? Well, you have 8 schools with 26 graders from each school. So 8 times 20 is 160. So square root of 160. So that's your standard error. And then your margin of error, you just go equals B7 times B8, because we want to multiply the critical value times the standard error, and that gives you your margin of error. So margin of error is 49825. Now the one-step method for finding the margin of error is what I showed you on the last slide. It's a command called confidence. So go equals confidence dot norm parentheses, and then you give the alpha level, which was 0.08, and then you give the standard deviation, which was 3.6, and then you give the size of the sample, which again was 160. Okay, 8 times 20 is 160, and so you have that value, and look, it equals the same as the margin of error that we calculated, using the critical value and the standard error. All right, and then once you have your margin of error, you're just going to go and take the sample mean, so that's in B6, and subtract the margin of error, which is in B9, and then you're going to do a sample mean, B6, equals B6, and then you add the margin of error, which is B9. So that gives you the two ends of the interval, 51.8 to 52.8 approximately. And that is our estimate, our confidence interval that estimates the average height of sixth graders in this district. All right, we're 92% confident that the true average height of all the sixth graders in the whole district, not just in the sample, but in the whole district, is somewhere between 51.8 and 52.8. All right, so this next situation is when the population standard deviation is not known. And this is a more common scenario. So in this case, instead of sigma, which is your population standard deviation, we're going to use our sample standard deviation, which is S, in the calculation of the margin of error. Now, we can't use a z-score, though, because the whole theory behind things is based on knowing the population standard deviation. So if you're going to use z-scores, that's all based on that. So we can't use that, so we're going to have to use a new type of score called a t-score, which is similar to a z-score. And this was developed by William Gossett, and he had a pseudonym student. So this is called student t's distribution, and it's when sigma, or population standard deviation, is not known. Now, if you notice on the graph, the t distribution is a little bit less high and a little bit more stretched out in the tails than the normal curve or the z distribution. Now, this formula that we have here, that's not what we're going to use for finding the critical value. We're actually going to either use a table that I'll show you in a second, or the t.inv command in Excel. So to find a critical value using the t-distribution, we need to know the degrees of freedom. The degrees of freedom is right here in this formula. Degrees of freedom is n minus 1. So it's the sample size minus 1. All right? So you need to know alpha, and you need to know the degrees of freedom, which is 1 less than the sample size. So here you see a table A3 that's in your textbook, and it is showing t critical values, and the rows are numbered and called degrees of freedom, but the columns depend on alpha. So if you had a 95% confidence level, alpha would be 0.05, and confidence intervals are always two-tailed. They're always two tails. So we're going to look at the area in two tails of 0.05. That would be the middle column. All right? And then whatever your degrees of freedom is, that will determine your row. So if we had area in two tails, or the alpha level is 0.05, and let's say the sample size was 12, then we'd go down that column to row 11, because the degrees of freedom is 1 less than the sample size. So that would be 2.201 for your critical value. Now, if you don't use the table, you could use the t.inv command. You just have to use the probability alpha divided by 2, put that first, and then give the degrees of freedom in the command. All right, now let's look at some examples. So this first example, all you have to do is find the critical value, t alpha divided by 2, for a 98% confidence interval if the sample size is 20. Now first, you do 1 minus 0.98 and get 0.02, and that's the two-tailed area. And so we look up in the table, the degrees of freedom is 20 minus 1, or 19. So if I switch to this, the sample, if the area in the two tails was 2%, because it was 98%, so 0.02 would be the area in two tails. I'm going to use the second column here, and I'm going to go down to when degrees of freedom is 19. So it's 2.539. That's our critical value, T critical value, 2.539. And so that's what is shown in this solution, 2.539. Now using Excel, if you had 98% in the middle, then you're going to have 1% on each tail, right? 98% in the middle, 2% on both tails, but 1% on each tail. So if there's 1% in the upper tail, then below that is 99% if you include the middle and the lower tail. So if you use the command t.inv 0.99, 19, because 19 is your degrees of freedom, that will give you the same value as you find in the table, although it gives a little bit more precision. You can look at example 1 on page 344 for a similar example for finding a T critical value. Okay, now let's say a quality control technician randomly removes 16 bottles of vinegar from a production line in order to test the pH level. The sample results give a mean pH level of 3.8 and a standard deviation of 0.8. Construct a 95% confidence interval to estimate the population mean. Now first we got to ensure that the conditions are satisfied. So do we have a random sample first of all? Well, yes, he's randomly removing the bottles from the production line, so we have that. Do we have independence in the sense that is there at least 10 times the sample size in the population? Well, 10 times the sample size of 16 is 160. And yes, there's at least 160 bottles in the production line. And then the third condition is you have to have that either normality of the original population or a sample size of at least 30. Now, we don't have a sample size of at least 30. We only have a sample size of 16. But do we have normality of pH levels? Well, because this is factory produced, and factory machines target a value, and they basically the values would be in a normal curve around that targeted value. We mentioned that factories and production lines will generally produce objects that are, in targeted values like the length and the width and the volume and the mass and all the rest of the condition or the measurements you could take are going to be normally distributed. But even if you just mention that we don't have a large enough sample size, but we need to, we have to assume that they're normally distributed. All right, then step 2, determine the critical value using table A3 or TINV. Well, we already just showed how to find that. Well, in this particular one, we have a 95% confidence interval and a sample size of 16. So if we switch to the table again, a 95% confidence interval would mean your alpha was 0.05 and the area in two tails, and then you just follow it down to row 15. Row 15 gives a t-score of 2.131. All right, so that's where this comes, 2.131 comes from. Now the standard error is the sample standard deviation, S, divided by the square root of n. So I'm using this margin of error formula. And so S was 0.8, and then the sample size was 16. So 0.8 divided by the square root of 16, that comes out to 0.2. Okay, and then you find the margin of error by multiplying these two things together. And so that's what I did here. 2.131 times 0.2, you get 0.426. And then we just go x bar, which is the sample mean, minus that margin of error, and x bar plus that margin of error. And I got the endpoints of 3.374 and 4.226. So that is our 95% confidence interval for the pH level for these bottles. That the average pH level is somewhere between those two numbers, we believe. So now let's show it on Excel. So I've got the same problem typed up here in Excel. And so first of all, we think about the sample mean. Well, it says that the sample mean was 3.8, so we'll put that in there in cell B6. And then the critical value, well, this is a situation where we don't know the population standard deviation, so it's got to be a t-score. And the t-score, yes, we did look it up in the table A3, and we found it to be 2.131, I think it was. But if you want to use the t.inv command, I can show you that. So we can go equals t.inv, and then parentheses, then the probability, that's the alpha divided by 2, I believe. So if it's a 95% confidence level, we'd be 0.05 divided by 2. And then your degrees of freedom, which is going to be 1 less than the sample size. So 16 minus 1 is 15. And so you do that and you get 2.131. Now that's negative because I forgot to put 1 minus. You got to do 1 minus the probability, the alpha divided by 2 probability. So I changed that, and now it's correct when you go 1 minus that. All right, so then that's the critical value. And then the standard error, we have to do that, the standard deviation of the sample, because that's all we know, the sample standard deviation, which is 0.8, divided by the SQRT square root of the sample size, which is 16, and that comes out to 0.2. And then the margin of error, we just multiply B7 times B8, and that gives you the margin of error. So that's the margin of error, but there's a one-step method for finding that margin of error, which avoids some of the calculations here. So you can go equals confidence dot t, because it's a t situation, because we have the sample standard deviation, not the population standard deviation. And then you give the alpha level. Well, if it's 95% confidence interval, then you're going to go 0.05 for the alpha level. And then the standard deviation is the 0.8 or 0.8. And then the sample size is 16. So just give those three things, and basically Excel figures out all of that other stuff. It figures out the critical value and the standard error and just multiplies them all. So that gives you the same answer that the margin of error doing it separately or the calculation separately gave you. All right, and then the lower and upper end will just go equals the sample mean B6 minus B9, just like we did before, and equals B6 plus B9. So that's how to find the confidence interval. So we're 95% confident that the true pH level of all the bottles in the production line is between 3.3738 and 4.2262. All right. So that's how quality control technicians could estimate the true pH level of all the bottles produced by the factory. All right, so what are the interpretations of a confidence interval? Well, in terms of a confidence interval for a mean, so on that last confidence interval we did, we could write, we are 95% confident that the confidence interval from the low end to the upper end, 3.374 to 4.226, contains the population mean pH level. This means that using this method to create many such confidence intervals, 95% of these intervals created from the sample means will contain the population mean mu. So again, the interpretation that I just mentioned can be illustrated with this picture. I put in a mean of a whole population of 3.7. Could be 3.7, 3.8, 3.9, whatever. But one of these confidence intervals, would be, it appears that 5 of these confidence intervals did not contain the true population value, and 95% of them did. And so, if I refresh this, you'll see that it won't be always 5. This time it was 4 of them did not, 4 out of 100 did not. Or, sometimes it could be more than that. It could be 7 or 8 or whatever. But that's the idea of a confidence interval. So the last item here is how do you determine the sample size required for a particular margin of error and confidence level? So let's say you want a certain margin of error. Let's say that person that's a quality control person in the factory wants to ensure that the pH level is to a certain precision within, within the margin of error. So they want a certain margin of error and based on a certain confidence level. Well, then you could put in these values and determine the sample size you would need. In other words, how many bottles you'd have to open and measure the pH level for. And so it would be the critical value, Z alpha divided by 2, times the population standard deviation divided by the margin of error, and then square that. And that would be your sample size. Now, if it doesn't come out to a whole number, you round up to the next whole number. Now, if you do not know the population standard deviation sigma, there are 2 options. You either find several values from the population and then use an approximation that the sigma is approximately the range divided by 4. And so that's one way to do it. The other way is to take several values from the population and just calculate the sample standard deviation and use that instead of the population standard deviation, and then just fill it into the formula. So that's a way to determine how big of a sample size you would need. Now, of course, it's going to be costly to open a lot of bottles of the vinegar, whatever that's being produced. So you want to be as most conservative as you want, so you could use this thing. All right. So that covers section 7.1 and 7.2 on confidence intervals and how do you determine the sample size for a certain margin of error that you want. All right, and then we'll have another video on the basics of hypothesis tests.